In this video, we're going to look at interpreting first and second derivatives. We know how to calculate them now, but what do they mean when we get certain values for these derivatives? We're going to look at the first derivative first, and there we often talk about the sign of the first derivative, whether the first derivative is positive or the first derivative is negative. We're also going to talk about this on intervals, and remembering that open brackets indicate that the endpoints are not included. If we have a first derivative that is positive on some open interval, then the conclusion we can reach is that the function is increasing. And that makes some sense. We can do some quick sketches. If we have a positive derivative at a point, then we have a positive slope on the graph of f of x against x. But if we continue that pattern where at every single point the tangent line has a positive slope, maybe gets close to zero but never quite, then we can see that there is a relationship between the function being positive in its derivative and the function itself being increasing. And of course we have a symmetric relationship. If we're told that the derivative is always negative, then the function itself is always going to be decreasing. The second derivative is a little more interesting. The second derivative, remember, is about concavity. So if we have the second derivative being positive, then what that is telling us, or what we can infer about the function, is that the function itself is going to be concave up. And what that means is if we have slopes, the slopes are getting more towards the positive side. And it can be anything in this shape here. We can also just talk about parts of the graph that might be like this. That would be a concave up graph everywhere, as with this one with a full curvature, concave up and decreasing, concave up and increasing. What we can see is that these two different pieces of information, the first derivative and the second derivative, are essentially independent. Here we can be decreasing and concave up, and here we can be increasing and concave up. So we'd have a mix of first and second derivative properties there. Concave down, same idea. That's where the second derivative is negative. And in that scenario, we'd have curves like this. Or again, possibly a curve that flattens out but is still concave down. Now we make a quick note that all of those examples dealt with non-zero values of those first and second derivatives. What can we say about the zero values? What happens when the first derivative of a function is zero? Well, if we talk about our function itself and we talk about the graph, if we pick a point on the graph and we know that we have the first derivative is zero, that means if we draw a tangent line there, that means the slope will be zero at that point. And what that can look like is a graph like so. So it could point to a local maximum, but that's not the only option. Let's extend our axes here and give a couple of more variations on the theme. If we have a zero slope, we might also have a point where we reach the zero slope for just an instant, then keep going up, and then do the same thing again. We might have another point, maybe down here. Let's clean this a bit. There we go. Where the slope at the tangent line at that one point is zero, but it might be a local minimum. If we highlight those points in those zero slopes, we can see a variety of different shapes, but they're interesting points on a graph. They tend to be significant points of interest in the sense that they're frequently local maxes or local minimums, or even some transition point here. You can actually see it's a transition from concave down to concave up. So a point of inflection is a frequent co-occurrence with the first derivative being equal to zero. It's also possible to have a really boring version of this as well, which is the graph is just flat. If you have a constant function, then the derivative is always zero, pardon me, and that tends to be less exciting and less interesting mathematically, so we tend to focus on these scenarios here, but it's worth noting you can have several points in a row that are all satisfying derivative equals zero, and then you just get a flat or horizontal line. The second derivative is a little trickier to see. What you can imagine is if you have an interval where the function is concave down, and it doesn't have to go to a flat point. So let's just say concave down here. On that interval, what we know is that f double prime will be negative. That's what the concave down relates to in the second derivative. And then if we transition, not going flat, but just changing the curvature, then on this interval, we're going to have the second derivative being positive. And if you think about what has to happen in the transition between those 2 points, or those 2 intervals, at that juncture here, you must have the second derivative equal to 0. And so there we see a point of inflection. So that's a very common occurrence. When we have the second derivative equal to 0, it is frequently a transition from one concavity to another, concave down to concave up, or vice versa. It doesn't have to be, though. You can also have concave down, and then it's hard to see the second derivative at a single point because it's so much about the changes and the transitions. But it could be concave down, then just straighten out for a second, and then go back to concave down again. That's a possible outcome for the second derivative equaling 0 as well. A little more subtle. Basically, there's no guarantee that you're going to get the point of inflection if you had the second derivative equal to 0. It's just one of the possibilities. We could also get a little more meta and look at the kind of scenario we looked at earlier for the first derivative always equaling 0. If the second derivative, the concavity, is always 0, that means the slope is not changing, and that gives us a straight line. If we drew this graph here, this would satisfy the second derivative equals 0 at all points. Typically, these are the scenarios we're interested in, but again, if you take a look at derivative rules, if you took 2 derivatives of a linear function, you would also find the second derivative is 0, and that corresponds to our understanding that there's no change in the concavity. There is no concavity for a straight line. Now, there is a little counterintuitive issue here at the transition points. We're just going to dive into this a little bit. Don't try to make too big of a deal of it, though. If you take a look at the function f of x equals x squared, it's fairly straightforward to find the derivative. It is 2x. Bring the power down front and subtract 1 from the power. If we then ask, where is the derivative positive and where is the derivative negative? Well, 2x is positive when 2x is larger than 0. Well, that's just when x is larger than 0. And we have the same kind of result for the negative side. That's going to be negative when 2x is less than 0. Well, 2x is less than 0 is easier to express as an interval simply when x is less than 0 itself. And if we sketch that out, what we would say is on this interval, 0 is the magic breakpoint. On this interval, but not including 0, f prime of x is negative. And on this interval, f prime of x is going to be positive. So where's the confusion coming in? Let's see. Based on this analysis, on what intervals would you say that the function is increasing? Which is close to the first derivative, but not quite. Take a look at those 3 options and select the one you like best. We'll pause the video for a moment. All right. Now here it really gets into technical definitions that are not a major part of this course, but there are definitions underlying this. Here's our function, f of x equals x squared. And the usual definition of increasing is defined by points. If I can pick 2 points on an interval and know that the point on the right is higher, then I would say the function is increasing from here to here, if I can do that for all the points. And it's certainly true that if we pick any 2 points to the right of x equals 0, we're going to get the higher point on the right-hand side. Pick these 2 points, this one's higher. Pick these 2 points, the one on the right is higher. But if we zoom in on the region right around 0, if I put a point at x equals 0 and compare it to any other point to the right, are those other points higher? Well, absolutely. As soon as we put any x in here that's not 0, that's bigger than 0, this is going to be larger. And so what we would say is we are increasing on the interval that includes 0. So a bit counterintuitive. The slope is positive just past 0, any points just past 0, but we'd actually say the function is increasing including the boundary point 0. And so that would actually lead us to B being the correct answer here. A little note on notation. Again, we would never say that a closed interval includes infinity. The square brackets and infinities don't go together, so we could rule that one out at the outset. The challenge is really deciding between these 2 here. Now again, that can feel odd because, again, going back to the last page, we said the derivative was positive on an open interval, and then we said the function is increasing on that same interval, but also including the endpoint. It is not a major issue in this course, but it is a kind of terminology and kind of challenge that comes up when we're trying to define terms like increasing and decreasing. It really becomes important to get a strong and clear definition for those properties, for those ideas. And then with a proper definition, you can easily answer these questions because you know exactly what you mean by increasing. Math 120 is a course that dives a bit further into these kinds of details. So if you enjoy that kind of intellectual challenge, that's an excellent place to look for this kind of reasoning and proof-based constructions. In Math 121, we're not going to get too worried about this. On a test, for example, if you said the function is increasing to the right of 0 on an open interval, if you said this was the correct answer, that would be fine. We're not going to get too fussy about what happens at precise points on ends of intervals when it comes to increasing and decreasing.